Music has often been defined as the art of organizing time with sound. It's a definition that holds true whether we're talking about a primitive tribal drum beat or the most sophisticated modern symphony. The one constant is sound. At every level of discussion, music must be based on sound, or we simply don't recognize it as music. Our recognition and organization of sound internally is subjective and is usually referred to as psychoacoustics. Yet, from a strictly objective perspective, sound is a measurable phenomenon that occurs outside the human organism. While even a cursory understanding of music requires an integration of both viewpoints, this interactive presentation focuses more on how sound and music work from an external perspective, physical acoustics, as opposed to psychoacoustics. From a physical perspective, sound can be defined as mechanical variances traveling as waves through an elastic molecular medium. These pressure changes travel outward in all directions from anything that vibrates mechanically and that is in contact with the medium. There are a lot of concepts contained in that definition. Let's back up and explore them one at a time. First, what is a molecular medium? A scientist will define a medium as a dynamical system that has the capacity to propagate a wave. But we can simplify that definition for the purposes of studying sound. A medium is really anything. That is, anything that we can touch and feel, anything made up of molecules. Solids, liquids, gases, all of these substances are made of molecules, and they all transmit mechanical vibrations, that is to say, sound. So, what isn't a medium? Quite literally, nothing. Empty space. A vacuum. A vacuum has no molecules, and so it can't transmit physical disturbances. Try the classic high school physics experiment of putting a ringing alarm clock in a bell jar and removing all the air with a vacuum pump. The ringing of the alarm clock goes silent because there's no molecular medium in the jar to transmit the sound. How about elastic? This term refers to the tendency of a substance to return to its normal state after being disturbed. Here again, everything is elastic more or less. Gases, liquids, and solids. Even something as seemingly unyielding as solid steel. Consider the elasticity of a steel spring or of a tuning fork. So, if everything is an elastic molecular medium to some degree, everything can transmit sound to some degree. The term wave is a favorite in all branches of physics, whether applied to sound or light or electricity or even earthquakes. It means a disturbance from a normal state of equilibrium that spreads through a medium. For example, think of a pool of water as a medium. Normally, the pool has a flat surface where every part is at the same level, equilibrium. However, if we disturb any part of the surface by touching it, we'll see rings of higher and lower levels spread out from the point we disturbed, waves. What's important in understanding the wave concept is that the water itself isn't traveling, only the disturbance. Although the pool example makes it easy to visualize the concept of traveling waves, Sound waves are not quite the same as water waves. In water, the waves are transverse. That is, the disturbance is at right angles to the direction of the wave's travel. However, in sound, the waves consist of small changes in air pressure rather than changes in surface height. These pressure changes are longitudinal. That is, the disturbance is in the same plane as the direction of the wave's travel. Sound waves in air are always longitudinal. That brings us to mechanical variances. Every physical substance is made up of vibrating molecules, or atoms. In each substance, these elemental particles are spaced apart from each other at set distances. In solids, the distances are highly restricted and usually set in a lattice-like structure where the molecules can't move past each other. The distances can vary if enough force is applied, but only by infinitesimal amounts, and they spring back to their set distances. In contrast to solids, the molecules in liquids and gases move about freely. In liquids, they jostle and slide past each other as you see here. And in gases, like air, they careen about chaotically, colliding and bouncing off of each other at some distance from each other. Yet, despite the seeming randomness, there is an average distance between molecules in gases. In air, that distance is about 10 molecular widths. This spacing makes it relatively easy to vary the distance between gas molecules. The force that causes this variance is called pressure. If pressure is raised or lowered beyond normal, the molecules pack closer together or pull further apart. Left alone, the molecules will return to their normal distance apart. Any vibrating object surrounded by air will pack the molecules slightly closer together, compression, when it pushes against them, and pull them slightly apart, rarefaction, when it moves back. These disturbances travel outward in all directions from the point of origin. These changes in pressure don't have to be very large to be heard. In fact, in the sound of a normal conversation, they're on the order of 1/10,000th of 1%. This means that if the barometric pressure in a room were 29.921256 inches of mercury, the international standard, sound waves would cause a change of only between 29.921242 and 29.921270 inches of mercury. That's far too small to be seen by any normal means. But we can represent these minute changes in pressure over time with a graph like the one shown here. As with the pool example given previously, it's important to understand that it's not the air molecules themselves that travel in sound. If they did, that would be wind, not sound. It's simply the changes in pressure, or, more exactly, the varying closeness of the molecules to each other, that radiate out from the source that make sound. In a single, unchanging environment, sound's speed is constant. For example, in static air at a temperature of 70 degrees Fahrenheit, sound waves travel at about 1,130 feet per second, or about 344 meters per second if you prefer. For musicians, this number is worth memorizing because it's often incorporated into useful formulas related to how music is made. However, the speed of sound is not a constant across different environments. It's affected by several factors. The most significant of these factors is the medium through which it's traveling. For example, the speed of sound in water is 4,756 feet per second, and in steel, it's 16,732 feet per second. In general, the stiffer or harder the medium, the faster sound travels through it. That means that sound travels faster through a diamond than through graphite, even though they're both composed of nearly pure carbon. But the denser the medium, the slower sound travels through it. So, sound travels much faster in aluminum than it does in lead. In hydrogen, it travels about 4,286 feet per second as opposed to 1,130 feet per second in air. Comparing speed of sound in different materials must balance stiffness versus density. Temperature also affects the speed of sound, although under normal conditions the variance is small compared to that caused by different media. In general, the higher the temperature, the faster the speed of sound. In air, the change equals only about 1 foot per second for every degree change on the Fahrenheit scale. There are also several factors worth mentioning that don't have any effect on the speed of sound. In contrast to temperature, air density has no appreciable effect. Also, contrary to many misconceptions, neither frequency nor amplitude have any effect. Furthermore, distance from source to receiver has no effect. Since the speed of sound is relatively constant in a constant environment, we can deduce that the faster the object's vibrations, the smaller the distance must be between each compression cycle. We can demonstrate the concept with the formula shown here. Understanding the interrelationship between frequency and wavelength can lead to some interesting practical applications. Instrument construction, for example. To resonate at a particular frequency, an open tube of air needs to be half as long as that frequency's wavelength. Here's a demonstration of that principle that uses only plastic pipe and a paintbrush to initiate the wave. In sustained sounds, molecular displacement is repetitive and is usually highly regular. The term regular in this case means that the compression-rarefaction cycle repeats exactly the same way at very evenly spaced time intervals. For example, for the note A4, the orchestra's tuning note, it repeats exactly every 440th of a second. This regularity in vibration is called periodic motion. When compression waves repeat like this, we hear the sound as an identifiable pitch. In other words, it becomes a musical tone. However, if there is no regularity, then the vibration is said to be aperiodic, that is, random. Aperiodic vibration produces noise. Acoustics deals primarily with the physical description and quantification of sound phenomena. Since sound is based on the transfer of mechanical energy through waves, any discussion of how sound works must consider the properties of these waves and how they interact with each other, and with external factors. The two primary descriptors applied to waves are frequency and amplitude. Combinations of two or more frequencies or amplitudes give rise to secondary descriptors, phase and waveform. Changes that occur to any of these descriptors as they continue are measured against the scale of time. In textbooks, these descriptors are often limited to the four shown here and are discussed co-equally because they mesh well with similar descriptors based on human perception. In acoustics, frequency is a measurement of the number of periodic waves that pass a given point in a given span of time. Human perception of frequency is called pitch. We must emphasize that although frequency and pitch focus on the same natural phenomenon, they're not equivalent terms. Frequency is objective, quantifiable, and external to the human organism, while pitch perception is an internal, subjective reaction primarily to frequency, but influenced by other phenomena as well. The most common unit of measurement for frequency in sound waves is cycles per second, or the equivalent term Hertz, named after Heinrich Hertz, a German physicist of the 19th century. Hertz is the more frequently used term. In some situations, a logarithmic measurement called cents might be preferable to compare two frequencies. A cent is 1/1200th of an octave, or 1/100th of an equal-tempered semitone. While performing musicians don't normally use this terminology, scientists find it useful in experiments dealing with tuning and intonation. A single wave cycle is measured from a point of equilibrium through maximum compression, back to equilibrium, maximum rarefaction, and back to equilibrium. The time that it takes to complete this cycle is said to be the wave's period. Assuming that waves are periodic, that is, tonal, not noise, period and frequency bear a reciprocal relationship as shown here. To illustrate this, the frequency of a tone with a wave period of 1/440th of a second is 440 Hertz. The period of a 440 Hertz tone is 1/440th of a second. The physical distance that a wave covers is referred to as its wavelength. Because speed of sound is relatively constant within a stable medium, wavelength is inversely related to frequency. That is, the greater the frequency, the smaller the wavelength. This reciprocal relationship is shown in the formulas here. A few examples derived from the above formulas are shown here. Relating frequency to wavelength is useful to instrument makers. Most wind instruments require a resonant air column half as long as the wavelength of the fundamental frequency they want to sound. The air column inside a common C flute, without a B foot, is 2.16 feet because its lowest note, C, at 261 Hz, produces a wavelength of 4.32 feet. Among orchestral winds, clarinet is the lone exception to this relationship because the closed cylindrical pipe that makes its air column needs to be only 1/4 as long as the fundamental frequency's wavelength. Amplitude is a measure of how much energy is contained in the compression or rarefaction of molecules that make up sound waves. The greater the difference from normal pressure, the more energy is present. This is true whether the change is positive or negative. Thus, the measurement is always an absolute, that is, positive, number. Sound pressure doesn't equate directly to the energy or intensity of a sound. Sound pressure decreases in an inverse relationship with the distance from a sound source, but sound energy decreases with an inverse square relationship with the distance from the source. The most common unit for instantaneous measurements of sound pressure is the Pascal. Although instantaneous measurements of sound pressure might be useful in some applications, such as checking peak sound levels, it's generally more useful to state an average sound pressure level over a period of time. This averaging is done through a mathematical formula known as root mean square, in which many instantaneous measurements are taken. Each measurement is squared, an average is taken of these squares, and the square root is taken from this average. When comparing sound pressure levels to other sound pressure levels, we use the decibel scale. This term was coined in honor of Alexander Graham Bell, inventor of the telephone, hence the capital B in the abbreviation. The decibel scale is a base 10 logarithmic scale in which each numeric increase of 10 represents a 10-fold increase in energy. This means that a 10 decibel increase equals 10 times the energy, but a 20 decibel increase equals 100 times the energy, and a 30 decibel increase equals 1,000 times the energy. This allows for a huge range of loudness perception, a ratio of 1 to 1 trillion. Although the spectrum of human frequency perception, a ratio of approximately 1 to 1,000, can be expressed easily in an arithmetic scale, a logarithmic scale is preferable when dealing with the far greater range of human amplitude perception. It's important to emphasize that while many people use the term decibels as if it were an absolute measurement, it really isn't. It's a relative statement of how one sound pressure level compares to another. Only when a reference SPL is specified does it become absolute. Often, a sound pressure of 200,000ths of a Pascal is implied when the threshold of hearing is stated as 0 dB. This at least gives some meaning to often seen tables like this. Sound energy, or intensity, is usually measured in watts per square meter. Like sound pressure levels, Intensities can be compared using the decibel scale, but there's a difference in what the decibels refer to. This difference can be shown in these two formulas. As in SPLs, decibel comparison of intensities has no external meaning unless a reference point is specified. Often this reference is implied using 10 to the minus 12th watts per square meter, or 1/trillionth of a watt per square meter as 0 decibels, the threshold of hearing. The table here illustrates the relationship between SPL decibels and intensity decibels using their implied reference points for 0 dB. The magnitude difference between the two measures of sound amplitude is obvious. Each level of change in pressure is matched by that level squared in intensity. A doubling of sound energy can be represented by a 3 decibel increase, whereas a doubling of SPL is represented by a 6 decibel increase. Loudness refers to human perception of amplitude and can be somewhat loosely quantified in phones or sones. Our sense of loudness is instigated by amplitude, but it's not directly proportional to it. It's often confounded by biological and psychoacoustical factors such as our perception of frequency. The equal loudness contours shown here, sometimes called Fletcher-Munson curves, illustrate the fact that in order to create a sensation of equivalent loudness, more amplitude is required at high and low frequencies than at our most sensitive range of 1,000 to 5,000 Hertz. To compensate for this uneven perception of amplitude throughout the audible frequency range, decibel measurements for audio are usually adjusted with a filter that roughly inverts the frequency response shown by the middle lines of this chart. This is known as A weighting. A weighting applies a smooth 40 decibel increase in sensitivity as frequency approaches 1,000 Hertz. For loud sounds, C weighting can be used, though it's not as common. C weighting applies a flatter response curve similar to the inversion of the top lines of the chart shown here. In periodic vibrations, and particularly in music, waveform is a graphic or mathematical representation of one complete vibration cycle. Vibration of an object or medium follows physical principles that can be described with mathematical formulas. Take, for example, the simple periodic motion of a swinging pendulum. Observation of its back and forth vibration shows that the momentum slows at the top of each displacement and accelerates through its center equilibrium point. This natural inertia of any vibrating object can be simulated with a formula using a sine function like this. Here's a graph of a single cycle generated by this formula. A sine wave, like the one shown here, represents a simple vibration. That is, one that's composed of a single frequency. However, nature is rarely that simple. Almost all natural objects that vibrate do so not only as a whole body, but also in many smaller parts that generate other higher frequencies. This is called complex vibration, and the many different frequencies are called partials. It's an interesting physical phenomenon that the partials of essentially one-dimensional bodies like violin strings and wind instrument air columns vibrate in parts that are integer related to the whole body. In other words, they vibrate simultaneously as a whole and in 2/2, 3/3, 4/4, 5/5, 6/6, and so forth. These fractional parts vibrate 2 times, 3 times, 4 times, and so on faster than the whole or fundamental vibration. Now that means that a 440 Hz tone from a musical instrument is also producing tones at 880 Hz, 1320 Hz, 1760 Hz, 2200 Hz, and so on. The integer-related partials produced by a one-dimensional body are often called harmonics to denote their special integer relationship. The lowest, or first harmonic, is often called the fundamental, and the others are known as overtones. Thus, the fundamental is the first harmonic, and the first overtone is the second harmonic, and so forth. In naturally created sounds, the higher the harmonic number is, the less energy it contains. They fade to inaudibility after about the 10th harmonic. Together, the phenomenon of integer-related harmonics is known commonly as the natural harmonic series. The natural harmonic series is by no means the only harmonic series we hear in nature, or even in music. Vibrating plates, like drum heads, cymbals, and even bells, are essentially two-dimensional, and they produce non-integer related partials when they vibrate. A typical vibrating timpani head, on which waves travel from center to rim, and also around various radial sectors, will produce partials something like this. The waveform they create is much more complex, and their tones less distinct than wind and string instruments. Timbre is how we perceive a waveform's complexity. The multiple vibration phenomenon means that any tone we hear from a musical instrument is almost always a combination of many frequencies, even though we identify it as a single frequency, usually the fundamental. As shown here, it's the relative strength of the harmonics that allows us to identify the body of a tone as that of a flute, an oboe, a violin, a clarinet, and so on. All tones, no matter how complex they sound, can be reduced to a collection of individual frequencies represented by simple sine waves. This fact is known as the Fourier theorem, after the famous French mathematician. The process of reducing a complex tone into its constituent partials and strengths is known as Fourier analysis. It can be performed easily by any modern computer with a digital signal processor and inexpensive software. Applying the analysis to the same tone played by several instruments clearly shows that it's the varying strengths of overtones that forms the basis for our perception of timbre. Sound is a temporally based phenomenon. It takes time for pressure waves to travel from a source to a receiver. All sounds last for a finite amount of time. All of the previously mentioned parameters, like frequency, amplitude, and waveform, tend to change throughout a sound's duration. Therefore, time itself becomes an important descriptor of sound. Time can be measured in absolute units of hours, minutes, seconds, or milliseconds, although in musical situations we often use relative units of measures, beats, and parts of a beat. These are called relative because the actual time that any beat-expressed event takes must be relative to how fast that beat is. Changes that occur over the course of a single sound, for example, an individual tone played by a musical instrument, are described as a sound's envelope. The term can be applied to any time-based mutation, but it's most commonly used for changes in amplitude and waveform. Envelopes are a major factor in helping listeners identify and infer meaning from a sound. The changes are measurable and are characteristic of particular instruments and performance styles. Take, for example, a guitar and a French horn, each playing A440. The spectrographs from Fourier analysis look quite similar, so if waveform were the only basis for discrimination, it might be easy to mistake one instrument for the other. But when an amplitude envelope is applied to the two waveforms, the difference becomes easily distinguishable. Often, envelopes are broken down into 4 parts for more specific discussion: attack, decay, sustain, and release. Sometimes we lump these parts back together under the term ADSR, an acronym synonymous with envelope. In an amplitude envelope, the attack portion refers to the length of time that a sound takes to rise from nothing to initial peak intensity. While the actual time varies greatly depending on the instrument and on performing style, it's usually measured in milliseconds, as these examples show. Musical tones tend to settle in after they reach the first peak amplitude. This is referred to as the decay portion of an amplitude envelope. The sustain portion is not necessarily constant, but can contain changes in amplitude as crescendo, diminuendo, or vibrato are applied. The release portion is the length of time that it takes the sound to fall to nothing after the note is released. While the concept of an envelope's parts might be helpful in describing and measuring a tone, the divisions are not always clear-cut. The two graphic examples shown here illustrate this. Envelopes also apply to changes in waveform over time, and thus our perception of timbre. One excellent example of this is how a vibraphone waveform mutates from an overtone-rich metallic sound at its attack to a nearly pure sine wave as it subsides.